Hello, everyone. I'm actually from a company called Klocwork, spelt incorrectly. That's 1,000 lines of code work rather than the more traditional English spelling. And we're from, it's a Canadian company from Ottawa originally. And in the UK, distributed by Emenda, who have a little bit of a booth, conspicuous by the lack of a backdrop indeed, which is somewhere in a parcel force depot. But come and talk to us afterwards if you have any questions, because I'm going to go through this relatively quickly. Anyway, yes, static analysis. So I've been doing this stuff now for quite a long time, having had a very deep background in dynamic testing, actually. So I've seen both sides of it a little bit. And what are we talking about when we say static analysis? Now, there may be some additions here that I've not got, but essentially static analysis really is kind of a concept rather than anything else. We sort of, certainly in most industries I tend to see these days, we think of it as a specific thing, but actually it means an awful lot of things. It's just the idea of doing something in terms of analysis of our code without running it, which is actually quite a broad concept. And there's also a sort of a subset of static analysis, which is static code analysis. Now, static analysis, therefore, being slightly bigger, also includes the idea of running analysis on binaries or object code and so on, and not on the code you were writing itself. Sometimes used in things like banking systems. So in terms of the kind of stuff that generates for us, what can we do with static analysis? Well, we've got all sorts, anything from coding style and refactoring up there to coding standard enforcement, metrics, going back to sort of Myers and McCabe stuff, defect finding and security checking, which is kind of an area where there's a lot of buzz these days. And also there's even things like IP compliance down there, which again is a form of static analysis, making sure that if you take an open source software, you've also met the obligations of the licensing terms. So there's all sorts of things that come from this core idea of static analysis. Now, apologies, because marketing got hold of the slides. And anyway, where in our industry did it all sort of spark from? Well, the kind of space that Klocwork are into, which is defect finding, of course, there's sort of a guy, Stephen C. Johnson there in 1977, which is about the time I was born, actually, coming up with some incredibly clever ideas on removing, well, undesirable bits of code, essentially, from what we were about to release. And that's where the term came from actually the sheep's flock, the idea of having lint on it that you didn't necessarily want. It was undesirable. So that's where it all started, and kind of things actually stayed the same for a long time. So from the late 70s until really the late 2000s, in the space I work in, there wasn't a great deal of development. Everything was done essentially at a unit level. And it was only then in the 2000s where there was a few tools that came to the world, essentially from various academic and commercial research, that came with the idea of actually looking at programs in their entire state and see if we can detect some extra issues. So runtime errors, interprocedural control and data flow analysis, it was called, essentially. Now, probably some people say, well, we did stuff like that a while longer as well. Okay, maybe. But certainly that's where it hit the mainstream. The problem was this stuff, then we had to wait for the results, and I'll come on to that topic in a moment. But the idea is that now we can do stuff, partial analysis and incremental analysis, to kind of speed these things up and get it as soon as we possibly can in our development stream. So, so in terms of structural code analysis, what we're talking about is essentially analyzing what the compiler will see as it produces the AST, the abstract syntax tree, for the piece of code you've written. So looking at that from a structural point of view, we can find things like, well, in there you've got an assignment inside a condition statement for an if. You may have not meant to do that, so it's kind of a suspicious, in some way, construct. Did you mean to do that, or did you not? And these tools were very much intended to be as a developer's tool, because they were running straight after you tested it compiled. I don't know if users tested in the right context there, but essentially, check that it's compiled, and then if it's compiled, can we also run some analysis through it to see if there are any other things we've missed? So that was kind of the original theory. So think of simple mistakes. We all make them as coders. I made a particularly high number, and you would quickly be informed of those errors and erroneous code. Whole program analysis, on the other hand, was kind of looking at the entire system. So these are the things where we're using some sort of sophisticated inter-procedural control and data flow analysis, and it's the kind of stuff that typically you wouldn't spot with a code review. So it's running across multiple units and so on. Things are coming back from the outside. Now, if you're designing by contract and so on, you're going to set things up so you know what should be coming back and so on. But there's a lot of people that aren't in that kind of level of programming from the start. And so in those cases, we can't easily see. We try and do it with a code review and actually try and spot where there's mistakes. But it's not that easy to see across 5 million lines of code. So stuff that's difficult to spot, these interprocedural control and data flow analysis. And it's all sorts of things like buffer overruns. And notice that many of these have also got a security implication, which is where the world is seeming to go a lot these days. Buffer overruns, memory leaks, tainted data coming from the outside world being used for something inside our program that we weren't checking. We didn't check it for certain levels of a range. Now, that's kind of what is static analysis. Why would we use it? Well, I think very conveniently this has been covered a little bit. Thanks, Barry. So rockets blow up, cars crash, whatever. Why else? Well, it's our reputation. The problem in today's world is that everything seems to be rather connected. So when we have an embarrassing mistake, like we released, let's say, an Apple iPhone with some communication stack protocol issues, everyone knows about it. And so it gets expensive for our reputation. And actually, in a lot of the industries I work with these days, it all rather comes down to money. Now, I'm not talking necessarily, or maybe I am talking aerospace and defense. Certainly things do, if they go wrong, cost an awful lot of money, but safety probably is more of a concern. However, there's a lot of the world that is purely based on what's it going to cost me, either in my reputation or how many recalled units I've got. So, how can we also, well, other reasons we might do it is we actually have functional safety requirements. And in terms of static analysis, we can use static analysis for proving our compliance to coding standards and the like. So a number of these standards now also require that, thinking ISO 26262 in particular for automotive software. So there are some requirements on our code to be written in such a way that it's considered defensive and somehow careful from the very beginning. And this would normally use a coding standard. And again, static analysis can help us with that. Generally, and this borrows your slides now, generally if we're looking at the V model for software development, we see lots of things about testing or verification, if you will, of various levels of design versus what we've produced down here. And there's no mention of static analysis in the majority of the V models or whatever you would see inside a standard functional safety requirement. But, of course, if we let bugs trickle on up here, the more expensive it gets. So if we can find them down here, the more money we save. So in other words, if I were to write a book these days, now when I was at university, if I ever wrote, now I'm not pretending I wrote War and Peace at university, but if I wrote anything, I would typically write it. Maybe I was using a nice Word editor or something from Microsoft. And then at the very end of that, just before I maybe went to the submission, I'd run a spell checker through it. And of course then I'd have problems to deal with right at the end, which was a little bit annoying and possibly expensive in terms of time. These days we don't do that. We get a little squiggly line underneath what we've just written, and it tells us, oh, by the way, that's a spelling mistake or a grammatical error, which are incredibly numerous in my writing. But anyway, the point is we work in line. It tells us straight away we have a problem. So that's a good thing. And the problem with whole program analysis was we need a whole program or something that builds for it to work, so we had to wait till everyone checked in the code and we could run something on which we could then analyze. So the problem with that is that when Klocwork was first designed, it was running somewhere around here. After you'd checked in, after you'd finished writing your code, after you'd even done some unit testing in some cases. So that was obviously a problem because all of our defects are coming here. In terms of coding defects, they're being introduced there, and we weren't finding out till here. The cost was relatively high. So what we want to be able to do is analyze there. And that's really what we can now do by doing it in a partial incremental analysis on a desktop before you actually check your code in. Also applies to Agile, which is going to be, I guess, the topic of the next talk. if we have bugs building up in our agile cycles, sooner or later the momentum starts to slow down whilst we fix those before we do our next cycle. And of course, again, that's going to slow down the overall process and maybe even fail the process. So the sooner we can find the bugs cheaply, so the simple mistakes, the better. So it's all about how much we can find and how quickly we can find it. And who? Conscious of the time. Who should we be checking this code? Well, the developers. They're the people writing the code. So if they're writing the code and they're not in a particularly formal environment, where they haven't got very, very strict rules on what they're writing and so on, if we can help them find bugs very, very quickly that they're introducing either in their code or implicating on the rest of the code that's been written, we're going to help save some money. Okay, so that's all the good stuff, but what can't we do? Well, for some people, obviously there's some significant points here. We can't verify any form of runtime behavior, so we're not proving anything, generally with a static analysis tool. Now, there are a few exceptions, but they're not real static analysis tools. So the code is not, there's a couple of looks there. The code is not executed. That's the key point. So that's the first thing. So what can we actually prove? In the terms of Klocwork, we're not trying to prove anything. We're trying to help you find bugs as soon as possible for as little cost. Can't guarantee we found all of them. A good dynamic test will help you with that. But what you don't want to do is waste time dynamic testing something that you could have found problems in earlier, and therefore there's no need to go back through a change control board, opening up your code, fixing something that we could have found much earlier in the cycle, which applies also, as we heard in the first talk, to aerospace and defense. If no coding errors are making it through to the engine test, it's saving you a lot of money. You don't want that. And the same applies. Yeah. So the other area you can help is in terms of verification to coding standards and so on in functional safety. So there is a small element of something that's audited there, essentially proving that you followed the MISRA subset, or you followed part of the MISRA subset, or whatever you defined as appropriate for your requirements. So Klocwork, in terms of its certification, is certified for, now for those of you in aerospace and defense, this stuff seems a bit weak. You're not allowed to just have a pre-qualified tool for usage. But in other industries, where there's perhaps not quite the same safety requirements, you are allowed to have a pre-qualified tool, and as long as you follow the safety manual that's given with that, you do not need to re-qualify the tool for use on those projects in terms of proving the coding standards and so on. And then obviously from the extensibility side, also cover the MISRA guidelines and things like that. Okay.
Okay, thank you very much.
Yeah, thank you. No worries.